saw in our parent function of the reciprocal function that looks like this, that we have this discontinuity. It's not a polynomial function because it breaks. It's not continuous. And so there are going to be asymptotes on your rational functions. And so the domain restrictions that you're looking for are going to be, the domain will generally be all real numbers, except those values that give 0 in the denominator. And you're going to find these domain restrictions before you do any canceling. Okay, because these will, and the canceling, by that I mean canceling the factors. Okay, because depending on whether you can or cannot cancel the factors, it's a different type of discontinuity. Okay? So if you have factors in the denominator that do not cancel, these are going to be vertical asymptotes. Okay? If you have factors in the denominator that do cancel, you're going to have holes. Okay, so you have to be able to distinguish between these two. Okay, and so it involves finding the factored form of your numerator and denominator, and then identifying which of those factors. So every factor that's in the denominator to start with is a domain restriction, okay, whether it's a vertical asymptote or a hole. Okay, but if they do cancel, then you identify those as holes in the graph. If they don't cancel, then you're going to sketch in and identify them as vertical asymptotes. Okay, so if you look at this first example right here, you have x minus 6 over x squared minus 9. Okay, if you were to think of this in its factored form, x minus 6 over x plus 3x minus 3. Okay, once we look at it in the factored form, we can identify the domain. The domain restrictions are what values? Okay, so really what we're looking at is our domain is all real numbers, x not equal to plus or minus 3, correct? And now it's going to ask you to enter your answer in interval notation. So the way that you represent multiple intervals is you go from negative infinity to the lesser number, negative 3. And then you go from negative 3 to the next number, 3. And then you go from that number all the way to infinity. And because you have multiple intervals, you'll use the union of set symbol in between them, which is a capital U for this system. And so that would be your domain. Okay, now, are there any holes in this function? We have two vertical asymptotes. We had factors that did not cancel. Do we have any factors that got canceled here? No canceled factors, right? I didn't cross anything out, and so there are no holes. Okay, let's look at the second example. Okay, in the second example, it's already written as factors. Okay, so when I look at my undefined values, my domain restrictions from the factors in the denominator, where do I know my domain is restricted? It's all real numbers except for 6 and 1. So I need to restrict these using interval notation. I go from negative infinity to the lesser number, which is 1, and then from 1 to 6, and then from 6 to infinity, union of set symbol in between each, and that would be my domain. And then were any of these factors canceled? Once again, no. So there's no holes. Okay, you only have vertical asymptotes at those. Okay, when we look at this final example here, when you write the factored form, we have x minus 1 over x plus 1, x minus 1. And we identify our domain before we cancel, right? So when we look at our domain restrictions, what values here do we have to restrict from our domain? X can't be plus or minus 1, so we go from negative infinity to the lesser one. From that to the next one, and then to infinity. Union of set symbol in between. And there's our domain. Once we identify this domain, what we can now do is look to cancel any factor. So when we cancel this factor, the vertical asymptote exists at x is negative 1. Okay, but because this factor, the x minus 1's got canceled, there's going to be a hole located where? At an x value of 1. Okay, whatever value would make, or in this case, whatever value would make that canceled factor equal to 0. And the idea behind where that hole exists is most of the time you're going to be asked at what x value the hole falls. But if you were asked what is the ordered pair that corresponds to that hole, basically the ordered pair would be an x coordinate of whatever you solve for, and then you would take your function and evaluate at that point, and that would be your corresponding y. Again, does that make sense in the way I've described it? Okay, so if you want to find where the hole exists, there is going to be a hole in your graph. Okay? And so if you looked at a graph that was sketched in this way, let's say you had a vertical asymptote here and here. Okay? And so let's say the graph wound up looking like this. Okay? And let's say it told you there was a hole at the point, let's say 3. So at x equals 3 right here. Notice there's not an intercept here, so the hole's not going to exist on the x-axis. It's going to exist in your graph up here when x is 3. And so the way that you can find the ordered pair of this coordinate is 3. And then whatever our function is evaluated at 3, and that will give you your corresponding y, right? It's f of 3 is the y that corresponds to the x value of 3.